Hi, welcome to my channel, JaberTime. Today I'm going to talk about the directional derivatives and the gradient vector. Directional derivatives and the gradient vector. If z equals f of xy, the partial derivatives are f of x, or f with respect to x, derivative with respect to x, as you could see, will be the limit when h approaches 0 of f of x sub 0 plus h y sub 0 minus the original point, which is f of x sub 0 y sub 0. Since you're going with x, as you could see, we have x1 and x2 or changes or delta x. Same thing applies for y. You'll be focused on the y. This is kind of like y2, y1, and the difference between them, which is a small amount, h. These are called rates of change of z in the x and y directions. That's in the x direction, and this is in the y directions. In other words, in the direction of I and j. Now, when you have a surface S like this one, and you want to find the derivative of this tangent line, which is called t. That's not in the direction of the x-axis or the y-axis. It's in the direction of some vector being called u, directional vector. Suppose that we now wish to find the rate of change of z at this point, which is f of x sub 0 y sub 0, in the direction of an arbitrary unit vector u equals a and b. So u has the components of a and b, and this is a lengthier one. I'll show you more graphs in just a few minutes. This is like a scalar multiple of a vector u. So we want to find, as you could see, the rate of change of z at the point x sub 0 y sub 0 and actually z sub 0. To do this, we consider the surface S with equation z equals f of xy, and let z sub 0 equals f of x sub 0 y sub 0. So the image of this point, without mentioning the 0, will be up right here. The point P x sub 0 y sub 0 c sub 0 up there lies on the surface. The vertical plane that passes through the point P in the direction of u intersects S in the curve C. We talked about that in the previous videos. Okay, you see this curve C? So we talked about the curve when we fix x and y, but this time we are going not with x or y, we're going with the directional vector called u. And that will be the tangent line that we are concerned about in this video. So the slope of the tangent line t to the curve C at the point P is the rate of change of z in the direction of u. This summarizes the whole idea of this slide. Earlier we talked about T1 and T2 in a previous video, and the slope of T1 and the slope of T2. Same process, but since this is in a different direction, and that's why this section is called directional derivative in a direction of some vector. It doesn't have to be x or y. And this is more detail about what is going on down here. This is the u vector, has the components a and b, or differently sine, cosine theta, and sine theta. So if you're going from point P to point Q, or P prime to Q prime, you will have to multiply this by a scalar called h. So this is u, this is hu, where h is a scalar. Now the components will be hu and HB if you're using A and B. Of course, if you're using cosine and sine, that's going to be H cosine theta, and this will be H sine theta, which is all mentioned right here. Okay, so that's a directional vector. For some scalar h, therefore, we have the difference right here from x sub 0 to some x will be HA, and the difference in y will be HB. So x will be x sub 0 plus some difference called HA, and y will be y sub 0 and some difference called HB. Delta z over h equals z minus z sub 0 over h, which is f of. Now we are changing in both directions to go from the first point to the second point on the directional vector. We notice that we have two components, x components and y component. X changes and y. This is kind of like x2 and this is x1. This is your new location, and the y's will be the same thing. That's your y1, and that's like your y2 when we start later in earlier in calculus 1 talking about x1 and x2 and delta x. If we take the limit as h approaches 0, we obtain the rate of change of z with respect to the distance in the direction of u, which is called the directional derivative of f in the direction of u. The directional derivative of f of or at x sub 0 y sub 0 in the direction of a unit vector u is. This is a directional derivative, so not like the previous video going with x or y, t1, t2, we are finding the derivative at that point in the direction of a unit vector u. This is the formula that we are referring to. Of course, if the limit exists. Z equals f of xy. The partial derivatives fx and fy are, fx will be, if you notice here, the x changes and the y does not, because we're going with the x direction. The same way for the y changes, but not the x. And represent the rates of change of z in the x and y direction, that is, in the directions of the unit vectors I and j. The directional derivative of f at x sub 0 y sub 0 in the direction of a unit vector, which is AB, is, one more time, feel like I'm repeating myself right here, but just want to emphasize that there is two things. Either you go with u, which has two components, or you go with x by itself, or you go with y by itself, if the limit exists. Kind of like a summary of what we were talking about from the previous few slides. Now, if u equals I, which is 1, 0, then dif, or being called fx, and if u equals j, then the derivative that we're looking at only here is in the direction of y, which is called fy. In other words, the partial derivatives of f with respect to x and y are just cases of the directional derivative that covers both. Theorem. If f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector, being called a and b. So the directional derivative will be the derivative with respect to x times a, where a is the first component of the unit vector, plus fy, or the first derivative of f with respect to y, times the b component or the second component of the unit vector. And if you're using u as cosine and sine, that's going to be pretty much the only difference. Here's an example. F of xy equals x cubed minus 3xy plus 4y to the second. We're going to find the directional derivative when the angle is 30 degrees or pi over 6. And we're going to find the directional derivative at the location 1, 2, at the point 1, 2. Just applying the formula straightforward for more practice. I have the function right here. The directional derivative will be the first derivative with respect to x times cosine theta, which is pi over 6 now, and the first derivative with respect to y times sine theta, which is pi over 6 for now. And if you take your time and simplify, you will end up with the following. Sine 30 is 1/2. Cosine 30 is rad 3 over 2. Derivative with respect to x will be 3x to the second minus 3y. And the rest will follow from the first derivative with respect to y. That's going to be 0. That's going to be minus 3x. And that's going to be 8y. You could see the 8 right here, and you could see the y. Now to plug in 1 and 2, all what you need is just plug in 1 for x and 2 for y, anywhere you go that you have to, and that should do it. This is the final answer for the second part. Writing everything, I don't think I need to read everything right here with the numbers. You could see it just to save some time from the video. It's kind of a lengthy video also compared to last one. Even the coming one on coming section, it's actually more than this, about like 20% more. The gradient vector. The directional derivative can be written as a dot product. That's interesting. This is the directional derivative formula. We know it. We saw that earlier. But look at it. It's like a multiplication here of two things and a multiplication here of two things. If I could take it back as a dot product, I could see it coming from here. And I'm keeping the colors to show you that if you multiply this by this and you multiply the second part by the second part and you put it right there, this is actually the answer for a dot product between two vectors. This is an interesting vector that has a lot of use and applications. So we're going to give it a name in just a second. So this could be also referred to as the vector u. The first vector right here in red has a special name. It's called the gradient of f. Grade of f, or delta f, or del f actually, not delta. Delta will be the other way around, and that's what we call it. Definition. If f is a function of two variables, x and y, then the gradient of f is the vector function, defined by the following. So del f is a vector function of fx and fy. Differently, it's a vector function df dx. That's fx right here. I'm reading it in short, fx, instead of like the first derivative of f with respect to x. I, because those are vectors I and j, so you could use this symbols or you write I and j. The directional derivative of f in the direction of a u vector, a unit vector u, is now the dot product between the gradient and the unit vector. we write this in short. That's the gradient, and that's a unit vector. Here's an example. If the function that we have, fxy equals sine x plus e to the xy, then the gradient will be just finding the derivative with respect to x, the derivative with respect to y, and put them where they should be, which is, as you can see right there, vector notation. That's fx, the first component, and that's fy, the second component. The derivative of this with respect to x will be sine x will give you cosine x. With respect to x right here will give you e to the xy using chain rule times the derivative of this with respect to x, which is y, as you could see. The second component will be the derivative of this with respect to y, and this will cancel, and that will give you x e to the xy. Now, if you want to find the gradient at 0, 1, all what you need to do is plug in 0 for x, plug in 1 for y, and simplify, you get 2, 0. Find the directional derivatives of the function fxy equals x to the second y to the third minus 4y at the point 2, negative 1. In the direction of the vector 2i plus 5j. Well, first we find the gradient, which is the derivative with respect to x, the derivative with respect to y. We are not given the unit vector. They called it v, and you could tell that this is not a unit vector. It has sides of 2 and 5, so we need a unit vector. To do a unit vector, we just find the magnitude and divide this vector by its magnitude to make it smaller to a unit of 1. And this is how you do it. 5 squared is 25, 2 squared is 4. So add them up, that's square root of 29, which is the length of this vector v. So you divide the components by the length of the vector v, and that is a unit vector. Now I have whatever I need is the gradient and the unit vector. Since they want me to find the directional derivative of the function at the point, we're just going to plug in the point to negative 1. In the formula of the directional derivative, which is a dot product between the gradient and the unit vector. And plugging in right here 2 and negative 1, 2 for x and 1 for y. And in the u part, I have a unit vector right there. We know how to do the dot product. We multiply components and we add, and that should do it. Next, if you want to move to 3 variables, the directional derivative of f at x sub 0, y sub 0, z sub 0 in the direction of a unit vector u equals abc will be the following. This is like a slope of a tangent, as you could see. In calculus 1, this will be called like f of x plus h, y plus h minus f of x and y over some h, some difference. In vector notations, because it's kind of lengthy to read, we just write the directional derivative of f in the direction of the unit vector u at x 0. But if you notice right here, the font is bigger than those small x's. It represents a vector. So in general, this will be x sub 0, and this will be x sub 0 plus the difference from the scalar h times u, where u is abc. So x sub 0 will be x sub 0 y sub 0 if n equals 2 in 2 dimension, and in 3 dimension it will be x sub 0 y sub 0 z sub 0. The directional derivative as a dot product will be multiplying f of x times a, fy times b. I said f of x is fx, and fc times c. The gradient will have 3 components. In short, we have the del, or the gradient, equals the vector that has the components fx, fy, and fc. And that's another way to write it down. And the directional derivative will be the dot product between the gradient and the unit vector. Maximizing or the directional derivative. Like, in other words, if you are at single point on the surface, if you change your direction, you might be going down faster, so you have a slope that is different. The question here is, what's the maximum slope? Should I go 45 degrees? Should I go like 42 degrees? And things of that nature. Maximizing the directional derivative. Suppose we have a function f of 2 or 3 variables, and we consider all possible directions or directional derivatives of f at that given point, which is I just mentioned in a different way. These give the rate of change of f in all possible directions. In which of these directions does f change fastest, and what is the maximum rate of change? We know that the directional derivative of f in the direction of the unit vector u is a dot product between the gradient and the unit vector u. But we remember from previous sections that we could write the dot product in terms of the angle theta this way. This is the magnitude of the gradient, this is the magnitude of the unit vector, and this is cosine the angle in between them. Well, this is positive and this is positive, or non-negative in other words, and cosine theta could be positive, could be negative. When theta equals 0, we get cosine 0 equals 1, which is the max. So to maximize the directional derivative, you need to have this going on, which means those two vectors, u and del f, should go in the same direction. They should be parallel because the angle between them is 0. The maximum value of the directional derivative is this right here. Why is that? Well, if I go 0.9 here, we're not going to get the max. So we're going to make this 1 to get the max. And this is a unit vector. This is a 1. It's not going to be more than 1 or less than 1. So we want this to be 1. And this is already 1. So this will make the difference and will give you a higher value on the left, which is called directional derivative, or lower. So the maximum value of the directional derivative d of f of x in the direction of u is the magnitude of the gradient vector. And it occurs when u has the same direction as the gradient vector, which I mentioned up here. That is when theta equals 0. If f of x y equals x times e to the power y, find the rate of f at the point 2, 0 in the direction from 2, 0 to half and 2. Now here's the gradient. We find the derivative with respect to x and the derivatives with respect to y. We use the product rule, as you can see. With respect to x is going to be e to the y. With respect to y, this will act like a constant, so it's going to give me x e to the y. the gradient at 2, 0, just by plugging 0 and plug in 2, we have e to the power 0 because 0 is y, and this is e to the 0, and this is 2 up front. Will give me 1 and 2. The unit vector in the direction of PQ, where PQ is negative 1.52 is. Now, the vector that goes from P to Q will be like, 2 minus 0, that's a 2. Half minus 2 is negative 1.5. But this is not a unit vector, that's a V. That's a directional vector, but it's not a unit vector. So what we want a unit vector. We find the magnitude, we divide both components by the magnitude and simplify, and I have the following: minus 3/5 and 4/5. So the rate of change of f in the direction of from P to Q will be, it's called the rate of change, which is the directional derivative. We do the dot product between the black marker and the blue marker right here. This is the gradient, and this is a unit vector. We just do the dot product and take care of it. Negative 3/5 plus 8 over 5, which adds up to 1. 8 and negative 3 is 5. 5 over 5, which is 1. Part B says, in what direction does f have the maximum rate of change? And what is the maximum rate of change? Well, the maximum rate of change will have the direction of the unit vector, and will have the value, the maximum, as the magnitude of the gradient. So it's going to go in the direction of the unit vector. Remember when we talked about it's going to be in the same direction when u and the gradient, they have a 0 angle between. And now that's what we have. So, or differently, I could say the following: in what direction does f have the maximum rate of change? Well, it's going to be in the direction of the gradient. The gradient and the unit vector will have a 0 angle in between them, and the maximum rate of change will be the magnitude of the gradient, which is in this case square root of 5. That should do it. Thank you for watching, and I'll see you next one. Thank you. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.